A CWELD element connector is one of the 1D element connectors that are often used in representing spot welded joints in a welded structure. There are several important steps required in adopting the element using Hypermesh software. This tutorial aims to demonstrate the steps. The convergence test is used to select suitable elements for meshing the structure. The welded structure is organized into two components, which are hat for the upper part and plate for the lower part of the structure. Next, the CWELD element connector is selected and used to represent the welded joints. The element is available in menu pages under 1D elements. Under the main menu, Spot Weld panel is selected, and then under sub-panel of using nodes, node to node is used to create the CWELD elements. The welded structure can be viewed with wireframe elements. This way allows the nodes identified for CWELD elements to be easily seen on the upper and lower component of the structure. Identifying the nodes should be carefully carried out, so that the selected nodes accurately represent that of the physical spot welded structure. Failure to do so will result in a large error in the comparison results of the finite element and experimental model of the structure. The CWELD element connectors are then organized into the component. 10 CWELD element connectors are used to model the spot welds along both flanges of the hat plate structure. The next step after modeling the spot welds, the material properties of the welded structure are assigned. The welded structure is made from a mild steel sheet with a thickness of 1.5 millimeters. Isotropic material and card image of Mat 1 are used to define the material properties of the model. Then the mild steel properties are keyed in. The same steps used in assigning the material properties for hat and plate components are adopted. Creating the properties of the element connectors is the next step required. The changes in the color of the CWELD element, from yellow to white, confirms that assigning the properties to the elements have been successfully carried out. The properties of the hat and plate components also need to be assigned, but this time, it should be with a 2D element representation. The next step is the load collector, required for the boundary conditions and loads used in the modeling. EIGRL card image is used to calculate the natural frequencies and mode shapes of the structure. The range of the frequency of interest, within 0 to 1000 Hz, with 16 modes in total. Under the analysis section, the load collector, which is named as natural frequency, is selected. As a result, normal modes type and the method, struct, are created in the load steps section. The last step is using OptiStruct Solver for normal modes analysis. The results of the natural frequencies and modes shapes can be viewed on Hyperview. For this tutorial on normal modes analysis, only the elastic modes starting from the 7th mode to the 16th mode will be simulated. Different values of the natural frequencies of these elastic modes produce different mode shapes. Hopes that this tutorial could be useful and helpful for students, or engineers, or researchers, who are involved in modeling of spot welded joints. Thank you very much for watching.